Hello everybody. Welcome to the webinar on UMT TriboLab for automotive applications. I am Suresh Kuiry. I'll be presenting this webinar to you. I am a senior application scientist at Bruker Nano Surfaces Division, and I have been working with Bruker for almost 14 years and in this field for 30 years. Thank you for joining this seminar. Next 40 minutes or so, I am going to present various test methods and applications of UMT TriboLab, which is recently launched product from Bruker for automotive industries towards fulfilling test and evaluation objectives on tribology and mechanical test needs. Some interesting test results on friction, wear, hardness, Young's modulus, flexural modulus, scratch adhesion, and Mar resistance that are recently obtained using this particular tool will also be presented. At the end of the webinar, I will try to answer some questions. In case I cannot answer all the questions because of time limitations, I will email the answers later. Let's get started. Continuous innovation in the auto industries is mostly powered by energy efficiency, fuel efficiency or energy efficiency, whatever you call it, safety, environmental concerns, and some other factors. But these three are in my belief, the most important factors. Energy efficiency saves money, safety saves lives and properties, and environmental concerns deals with securing healthy and habitable conditions of our planet for us and our future generations. Therefore, these are considered to be the three important parameters for growth. To accelerate the innovation process, research and development activities are being vigorously pursued by automotive manufacturers, academia related to automotive research organizations, and vendors of automotive industries for their product. This activity helps them to stand out in the extremely competitive and dynamic global market. For product differentiation, extent of value additions, comparative data generations, and so on. UMT TriboLab, as a versatile tribologic and mechanical test platform, is leading such testing and evaluations endeavor effectively. Here are a few examples of auto components that can be tested for their quality and performance using UMT TriboLab system. For example, paints and coating can be tested for their scratch adhesion and hardness. Lubricants for their comparative Stribeck curves, so comparing lubricants from one another, which one is better and which one will be performing at a particular conditions. Clutch and brake materials, tires, piston ring and cylinder for their frictions and wear. Bearing for mostly wear, but friction as well. Elastomers, which are used in automobile industries, can be evaluated for hardness, usually shore hardness, which I'll explain later, and some other mechanical properties like flexural strength and stress. Engine valve, which is subjected normally to high temperature, could be evaluated for hot hardness. Windshield and mirror could be evaluated for scratch, mar resistance, stictions, and scratch resistance. There are two types of test methods. One is tribological and other is mechanical. Tribological test method includes mostly friction, it could be static or dynamic, and frictions, which is mostly static frictions, and wear and wear durability. The other kind of test normally performed for automobile components are mechanical type. It includes hardness, which is done by classical hardness methods, or I'll explain them again in subsequent slides in that particular section when I deal with mechanical properties evaluation. And it can also be obtained by using, more recently, kind of 15, 20 years back, instrumented hardness testing methods. And instrumented hardness testing methods can also allow us to obtain Young's modulus or elastic modulus. In the mechanical testing categories, we also have flexural stress strain behavior studies and elasticity in bending. And of course, we have scratch test for adhesions and Mar resistance, mostly related to thin film and coating, and some kind of surfaces like glass. Before I go into the test details, I would like to speak a few slides, maybe a couple of minutes on the tool itself. Here is a slide which shows the picture photograph of a tool, UMT TriboLab, we call it. It is built on Universal Mechanical Test Platform, we call it UMT, with precision control of load, speed, and position. This is most sophisticated and versatile tribology test system ever designed, with modular and innovative techniques, broadest capabilities, and it has unmatched ease of use. It's pretty easy to use. We'll explain how it is. It has real-time control and data analysis software to ensure high accuracy and repeatability of test data. Modular and innovative design makes Bruker's UMT TriboLab flexible. For example, it has a single motor that covers full torque and speed ranges, and that motor is actually all drives. I'll explain later all the drives. These drives is actually go into the lower positions where there is a self-centering coupler where it accommodates, and there is a precision-based ring on which all the drives goes. You do not need to use any tool to install this drive on the system. We call it tool-less clamping. There are 3 knob kind of stuff which you just rotate, put the thing in place, drive in place, and just rotate and it will lock it. It also has blind made electrical connectors so that you do not have to deal with any unnecessary electrical connectors and other stuff, so that it is not clumsy, it is clean and things like that. We also have a Tribo ID chip which acts as, to enact plug-and-play procedures. Whenever you connect a drive, the system automatically detects its it detects this drive, and it loads the optional features like what is the maximum speed in case of a motor, or if you are adding some other stuff like say some kind of some kind of environmental chambers, what is the maximum temperature it can go, and all other parameters it automatically loads. You do not have to pull it out from the system configurations. Actually, in short, it configures the whole system pretty easily whenever you just dump the drive and install it. It has broadest capabilities in force, torque, speed, temperature, and humidity ranges. As I explained, Tribo ID and there are another things called Tribo script. These two items makes the system very easy to use. Tribo ID automatically detects and configures components that are plugged into the TriboLab system. Tribo script, on the other hand, offers an enhanced and secure scripting interface with operator and expert modes of scripting environment for running tests at ease. At the same time, preserving the universality towards advanced test script development using test block methodology. There are 4 different types of drives available with this system, particular tool, to cover almost all kinds of tests, tribological and mechanical. First comes rotary drive, which can rotate along a vertical axis. And this is used for several tests like ball on disc, pin on disc, Stribeck test, thrust-cluster test, ring on disc type of test, and things like that. It covers so many STM standards, including Z99, G132, 3702, and things like that. We have a reciprocating drive, which is high-speed reciprocating drive. It can go up to 60 Hz. 60 Hz. And it has a stroke length maximum. It can go up to 25 millimeter based on at what load and what frequency we are running at. Block-on-ring drive is again similar to rotary drive, but it has a rotational axis perpendicular, not perpendicular like rotary drive, but along X directions, horizontal directions. This is mostly used for block-on-ring tests for evaluations of materials for wear resistance under extreme conditions, and also to evaluate lubricant, which are used for extreme pressure conditions. And finally, we have a linear drive, which is used mostly for scratch and other mechanical tests done on it. It can also be used for reciprocating tests, but only frequency is limited to very small, less than maybe 5 Hz, because it depends on how much stroke length we are using. It has a maximum stroke up to 120 millimeter. That is the displacement. We also call this as Y stage because it is installed that way. It moves the specimen or tool along Y direction. We have liquid and environmental chambers for all different drives. Here in this slide, you can see there are 4 chambers. Just I picked them up to show you. I didn't want to show all of them. So rotary liquid chamber is used for Stribeck test mostly, or any other test, pin on disc or say cylinder on side on disc and things like that, for evaluation of wear and friction, and also for Stribeck curve. And rotary heating chambers, which can go up to 150 or 350 degrees centigrade. We also have chambers that can go up to 1000 centigrade. Here is one rotary humidity chamber, which can control humidity up to 85% relative humidity. And we have environmental chamber for block-on-ring drive, recently designed, which actually takes into account the heat produced due to frictions. So it has a cooling facility so that you can control the temperature of the loop, which is used in this particular test, to a desired level. Now I should start with the actual test, which can be done using UMT TriboLab, starting with tribological test, which is friction test. Friction, as you know, it is the resistance force that one surface or object encounters when it is moved against another surface. On the left side, you can see that there is a block which is over another surface. When you slide this, friction acts at the direction opposite to the motion of the top block, relative motion, and friction force is actually measured using a sensor. Friction force, ratio of friction force, which is Fx in this case, to the normal force or vertical force, which is Fc, is actually friction coefficient or coefficient of frictions. We call it COF. It is usually denoted by mu. You know, traditionally, friction can also be measured by tilting the surface on an inclined plane. You just increase the angle of this inclined plane until the top block started sliding. You measure the angle of inclinations and you can calculate the coefficient of frictions. Mu equals 10 into alpha, where alpha is the limiting angle at which the top block started moving. But this is not very convenient method, although this has been described in some of the standards, most like in STM D1894, similar situations, but this is not very convenient. So what we do is in UMT TriboLab, we apply this load, normal load, by using a control method. It is on feedback, so you can really control this load. You apply a control load and make a relative motions between two couples, friction couples, and use force sensor to measure both the forces, lateral force or friction force, which is Fx, and the normal force, which is Fg, and software calculates the coefficient of frictions. In UMT TriboLab, you also have a facility to record the static frictions, or the friction force at the beginning of motion, very instant of beginning of the motion, which is usually higher than the dynamic friction. Here is what is explained. This is related to sledge frictions I am telling, because this particular block is being pushed or moved and Fx is actually measured. You see on the right side the plot of this Fx force along the distance is traveled this way. This is y. And you see at the very beginning when it start pushing, you see a static peak which is little bit higher than the rest of the data, which is known as dynamic frictions. From this friction force, if we take the ratio with the normal force, we get coefficient of frictions. Lubricant test, which is basically done by Stribeck curve, obtaining a Stribeck curve. Let me explain for those who would like to know more about Stribeck curve. Stribeck curve is basically plot of COF, coefficient of frictions, versus speed divided by load, normal force. And it plots for a particular lubricant. And you see in this case we had gone from 0.1 probably VYFG to 7th order of magnitude. And you see this curve, this is actually the Stribeck curve. At higher value of VYFG it rises. At lower value also it rises little bit. And in between there is a, like say, minima kind of stuff. So this curve actually shows three different regions. One is boundary regions, where these couples, friction couples, actually come in intermittent contact, or rather always in contact, boundary. And mixed, it comes with intermittent contact. And hydrodynamic, there is a thick film of lubricant present between the two contacting couples. So in hydrodynamic region, COF is increased because of viscosity of the lubricant. Whereas in boundary condition, this is really wear taking place between the two surfaces. Now you see the automotive components, like the piston ring, it actually operates from mixed to hydrodynamic regions depending upon which portion of contact it is, whether it is in top dead center or in the center and things like that. Engine bearing, which is mostly in hydrodynamic conditions, you have film, lubricant film. And if you look into cam and follower, they normally operate in the boundary and mixed region. In UMT TriboLab, we can also measure the electrical contact resistance between the two friction couple, between the two contacting surface. And you see the ECR data here. So when there is a film, ECR value is really high, meaning that there is a lubricant film present between these two contacting surfaces. And as we go to the boundary where actually two surfaces are in contact, you see ECR is dropping because two metallic surfaces are in contact and electrical contact resistance between them is almost zero. So this also can be measured and correlated. Stribeck curve is used to evaluate lubricant for their potential applications, in which region they work better. And also it is used for comparing two different kinds of lubricants, many lubricants, to find out which one will work in which region for which particular component better. Say for instance here, we have two lubricants, lube A and lube B. Lube A shows lower coefficient of frictions between in boundary and mixed regions compared to lube B. But in hydrodynamic regions, they are almost similar. So lube A will definitely perform better than lube B in boundary or mixed regimes of lubrication. Next is wear durability test. Wear durability test is basically done using a particular tip, maybe a ball, Rockwell diamond stylus, or some other tip, and it is done for especially for coating, mostly for coating. In some cases, maybe for some bulk material too, to know at what point the surface is getting actually wasted. So this is done by rubbing it in reciprocating motion, applying a load, and move the tip over the sample in reciprocating motions. Stroke and frequency can be determined by the user, and you measure several parameters including friction force. You can also measure electrical contact resistance, acoustic emissions, and things like that. Here is a plot. So here in this case, we applied 0.5 Newton load constant, and we rub it over 2 millimeter at about 2 millimeter per second, and COF is generated. After about 250 seconds of test, see COF went up very high. Looks like surface failed. So in these situations, probably we can say that this is the durability of this coating under such conditions of force and speed, velocity. Now this particular test, wear durability test, can be used again to compare different coating, how they will perform in actual service. Here is an example of another thick coating, which is about 40 micron thick, and here we monitored ECR signal. Excuse me, ECR signal. So when this coating, you can see we applied a load about 5 Newton, and coating started, COF started going up, and at this point, complete coating is gone, I mean totally wear worn out, and which is indicated by ECR signal which is dropping, meaning that that ball is under contact with the substrate which is again conducting. That means that it is completely filled at about 2,600 seconds of test, which is the durability of this coating. After finishing the test, this wear surface, wear scar was evaluated. We found that it is about 40 micron thickness, which corresponds to the thickness of the coating. So wear durability test can be used for evaluation of paints and other coatings, and also we can use for comparing their performance in the service. Actual wear test. Wear test, there are several different types of wear test. Those are listed in ASTM and other standards like ISO, and those things can be done using UMT TriboLab. But a particular interest for this webinar, I put thrust washer test, which is ASTM D3702, ring on disc test. There is a ring which comes on a disc. This could be a bulk material or it could be a coating too. And this disc is actually rotated. Disc is rotated and the force is applied. And wear happening on the disc, or in some cases the ring, is measured to find out the wear resistance of this particular material. Wear resistance is actually, or wear rate is expressed in such cases as specific wear rate, and this has a unit, millimeter cube per Newton meter. Millimeter cube is the volume of material worn out during the test in unit time and unit force. And unit time, in the sense, in this case we do not use time as a unit, we use the amount of distance traveled during the test. it will be clear when I show you a data here. Here you see there is a coating and which was tested by this ring on disc test method. This is the wear scar, you can see it, and this was the original surface, and this is the wear scar. So wear scar was evaluated after the test, and this test was done at 20 Newton, 300 RPM for 1 hour. And you see this was the depth of the wear. So volume of material removed from this coating was calculated, and total distance traveled during the test was also calculated, and divided by the load, we get a specific wear rate of 6.85 × 10⁻⁵ millimeter cube per Newton meter. And here is evaluations of the COF, which was more or less constant. Initially, there was something happened here, so it actually dropped. Maybe it hit a debris or something, and load was constant. UMT TriboLab has a special feature, which is, it is, since we can independently control the speed of the specimen or lower drive and speed of moving along X directions, which is mostly done by slider, we can control the linear velocity of sliding, which is a very unique feature, and it is very useful to study wear of any materials at constant linear velocity, because wear mostly depends on the velocity, linear velocity. And it can also be used, this particular methodology can be used to test some material which always moves, that contact tip moves on a fresh surface, not on the same surface again and again, which actually influence the test results. So this we call a spiral wear test with constant velocity. So here is just a presentation view graph where you see a load is constant load is applied about 120 Newton. 100 Newton. This is the load FC, which is in black in color, and we instructed the instrument or wrote a program where it says, okay, maintain 500 millimeter per second of linear velocity, no matter at what position the tip is, or contact point is, contact radius is. In this case, contact radius actually increases along these directions. So initially, see the velocity in RPM was higher to maintain that 500 millimeter per second linear velocity. It maintains all through, and it, as X increases, it goes outwards radially, the speed actually drops to maintain that constant velocity. This is another important feature which can be used for testing of materials, mostly polymer or some other materials for wear. Piston ring cylinder liner test. This is another important for automotive industries. This is basically called engine test, and this is described in ASTM Z181 in greater detail. So this is actually done, this particular test is done with the step loading. So you start with a certain load, this is FC, which is the normal force, and you maintain constant load for certain times, increase it in steps, go up to maximum. In this case, you went up to 1600 Newton, and then it went down. And measure friction at each point. This is done with the reciprocating drive, where it was running, in this case, it's 10 Hertz and 10 millimeter stroke. You see that this is an FX plot for each step, which started increasing. FX actually shows, because this is a reciprocating test, so you see a sawtooth kind of square wave kind of morphology for this particular plot. And if you do a first Fourier transform of this particular data, you see there is a 10 Hertz. We get that there is a frequency of 10 Hertz. Piston ring cylinder liner test is very important to study piston ring and cylinder liner for their durability, frictions, and performance. And it is very important to align them very precisely, and also the contact has to be some kind of compliant contact between the piston ring cylinder and the liner. those settings are done using a special tool developed here, which can be used to maintain the perpendicularity of this setup so that piston ring segment is installed perpendicular to the linear liner, and when it moves along perpendicular directions. We also have a bearing test with conformal contact. This is done on a modified block-on-ring drive, which is again which can be used for applying recirculated heated oil to simulate the actual service conditions. Next, I will move on to mechanical test, and I start with hardness test. Hardness is actually the resistance to plastic deformations of any materials, and this is done originally. Still it is being used. There are several methods like Brinell, Vickers, knoop, Rockwell, and Shaw. These are the more important. There are so many other methods too, but these are the major ones. And we have instrumented indentation test, as I mentioned earlier during the starting of this webinar. An instrumented indentation test which gives you hardness and Young's modulus from the load displacement data. We'll elaborate on those. Now, Brinell, Vickers, and knoop hardness are basically, these are indentation hardness kind of stuff. Here what we measure is we penetrate the material using some kind of tip. Say, for instance, for Brinell, we use a ball, hardened steel ball, and we apply a force to make an indent on the specimen, measure the indent diameter, in this case as small d, and use this formula to calculate the hardness. In Vickers, this tip is basically a square prism made of diamond, and we just make an indent. Indent looks like a square prism kind of stuff, square, and we measure the diagonal of this, take an average value. There may be tilt or some other kind of uncertainties. To deal with the uncertainty, we just take the measurements of these two diagonals, take an average, and use this formula to calculate, where 136 degrees is the included angle of these two surfaces of the indentation. And knoop hardness is similar to Vickers, but it has a little bit difference in the sense these diagonals are not, indented diagonals are not equal. So it has a rectangular prism kind of stuff. The ratio is about 1:7. And in this case, only long diagonal is calculated. And from the long diagonal data, you can calculate the knoop hardness. Compared to Brinell, Rockwell, and knoop indentation technique, we have Rockwell and shore hardness technique where we use differently. This is kind of methodology is measuring displacement. So in Rockwell, you use there are different kinds of indenter, mostly diamond, Brinell they call it, and this is done by applying a minor load initially on the surface, and then increase the load, add major load in it, then remove the load to a minor load, and measure the tip displacement from the initial minor load to the final minor load. And suppose the displacement is J, you use this formula to calculate the hardness. So the more soft the material is, this tip displacement will be more, hence hardness will be less. That's the way it calculated. In case of, say, Rockwell C scale, there are different scales. I think there are 10 scales or 15 scales. These are explained in STM standard. And in C scales, F minor is 10 kilogram force, F major is 150 kilogram force, and HRC is calculated taking K as 100, J is permanent tip displacement, and that is in unit of 2 micron. Shore hardness is also operates with similar principles, but it has different tip materials, geometry, and load levels. Load are virtually less, and it is primarily used for soft materials such as elastomers. Hot hardness. Hot hardness can also be measured using UMT TriboLab. Hot hardness is basically uh, hardness of the materials at high temperature. Some materials are exposed to high temperature in surface and they are supposed to maintain their mechanical strength at that temperature. So it is very important to measure the high temperature strength of materials. In this view graph you can see that this is for 347 stainless steel. If you increase the surface temperature, and the tensile strength, which is mechanical strength of that material, drops. It decreases. Now, so this tensile strength is basically hard. It is more or less equivalent to hardness with some multiplier. Now, usually high temperature mechanical properties of any materials, since this is a design criteria, when you design something for high temperature applications, it has to be evaluated, and it is usually done by mechanical or creep rupture test at elevated temperatures. These tests are inherently time consuming and very difficult. So hot hardness test using UMT TriboLab could be a faster alternative. And UMT TriboLab can operate up to 1000 degrees centigrade. Therefore, hot hardness can be measured using UMT TriboLab up to 1000 degrees Celsius. Engine valve is a material candidate which can be used for hot hardness measurement because this is subject to high temperature. Instrument and indentation test is basically done using a model colliver methodology, where the specimen is actually evaluated by using a tip with known geometry and applied load, and we get load displacement plot. From the load displacement plot, we measure contact stiffness at the maximum load and contact area, which is function of the contact depth, which is calculated based on this data. Only the unloading portion of the graph or data is used for these calculations, and hardness is measured as load divided by area. We get reduced modulus from the contact stiffness data, S by 2 to the power pi by A. And from this reduced modulus, we use this relationship, mechanical relationship, for elastic modulus. E is the elastic modulus of the specimen. Nu is the Poisson's ratio of the specimen. Nu I and EI are the Poisson's ratio and elastic modulus of the indenter. If you know, if all these things are known, three things are known, ER is calculated from this data, and E is found out, which is elastic modulus of the specimen. Next on this mechanical test is three-point bend test, which is very important. Three-point bend test is used for understanding flexural behavior of any material, flexural stress and strain, and also for modulus of elasticity in bending. Many components used in automotives are in service, they actually encounter bending load or bending situations. So flexural stress and strain and bending elastic modulus is very important parameters, are very important parameters. Here it is a three-point bend is elaborated here a little bit. So you have a specimen which is a beam kind of stuff with span length of L, and it has a depth of D and width of B. At the center of this beam, span, L by 2 distance from the one of the rollers. There are two rollers for supporting it, and the top roller for applying load. So it bends, the specimen bends. The maximum bending at the center from the bending moment diagram, if you look into, and that is maximum bending is noted as capital D. So we bend this, we test the specimens using UMT TriboLab, and we get force versus deflection data, FG versus D data. From that plot, we use this formula to calculate the flexural stress, strain, and elasticity in bending. Here is an example of three-point bend test done on polymer. I have another example for ceramic materials, and this is for a polymer. And you see this is the raw data, which is FG versus, in this case, Z, because Z is our G encoder reading, which gives you displacement, but this is basically capital D, that is the maximum deflection at the center of the beam specimen. And from this data, when we process this data using our data viewer, we get stress, flexural stress versus strain. And we calculate flexural stress at failure is about 86 megapascal in this case, and corresponding strain is 0.01, and elastic bending is about 1.25 gigapascals. Because that was a very elastic specimen, or say soft or ductile specimen. But if we look into a ceramic specimen, here plastic deformation is very less. This is the actual data, FG versus D plot basically. For a ceramic, it broke here, failed here. And in this case, at failure, we have 98 megapascals. Strain is much less than the polymer specimen. And elasticity in bending is about 13 gigapascals. Evaluation of paints and coatings for automotive industries. This comes under scratch test, and we will discuss this. So paint and coatings are basically, paint is relatively thick when we talk about paint. Its primary function is to prevent materials degradations during service, and this degradation happens because of corrosion, and it also improves, paint improves aesthetic. Coating is relatively thin, and it is used for improving the tribological properties such as friction, wear, and scratch resistance of the component, actual component. These things can be evaluated by using scratch test, which is part of the UMT TriboLab. UMT TriboLab has scratch test capabilities. It is fully conformed to STM C1624. It has wide force and velocity ranges. It has zoom in options to see scratch image immediately after scratching. It automatically takes the image of this entire scratch and plots it with the other data so that you can investigate what is happening in the optical images, where this actually scratch started and where delamination occurs and things like that. It can accommodate scratch tool, diamond stylus, Vickers, etc. And it also has automatic tilt adjustment. Scratch test, there are several different types of scratch test. One is particular interest is like progressive test, where load is increased progressively from a small value to a high value. Scratch width increases with load. And there is another one which is called zigzag scratch, where load is increased progressively, but at the same time, scratching tip is moved along the perpendicular directions to have a zigzag kind of motion. And there is another one which is constant load scratch test, unidirectional, where constant load is applied. And constant load scratch test with XY type, so it moves along Y directions, the next direction, and so on. But while moving, two subsequent Y motion is the spacing between those two motions are reduced. This actually gives an indications of crack susceptibility of the coating or the film. Here is an example of scratch test which is done on a painted panels. So load was increased up to say 45 Newton, and we measure resistance between the tip and the substrate which was conducting. Also acoustic emission data was also measured, and you see acoustic emission started showing up at this point onwards where actually coating failed. And also Fx value, that is the lateral force during scratching, was also started increasing. And at the same time, ECR data shows that it dropped down at this point, meaning that coating failed. So we get a corresponding FG value where this coating failed, and this FG value is actually reported as scratch adhesion strength of the coating. Scratch test also can be used for evaluating Mar resistance of any surfaces, say for instance mirror of automotives, and or glasses, So in this particular sample, bare glass specimen, it was tested similar to scratch methodology using a diamond tool, and you see it started showing up this mark on the surface of the specimen after about 100 millinewton load. Load is very small. In another instances, a different glass which shows this mark much lower load, about 50 millinewton. So this could be UMT. This type of test, like say Mar resistance test, can be used for comparing two surfaces, which one has better Mar resistance and things like that. We have another type of test which is available with the UMT TriboLab, is called scratch test with depth profile, and we say it is pre-scan scratch and post-scan type of sketch. Why it is like that? Because initially the sample surface is evaluated with the same tool, same tip, for its surface inclinations or some kind of other presence of features or whatever, with a pre-scan with a very small load. And then next step is to scratch it, and then after scratching we post-scan it, and each time we measure the depth profile. In this case, this is the scratch data. Where it failed, you see we have measured displacement, that is particle displacement, using a cap sensor, acoustic emission, and lateral force. And it was scratched using a linearly increasing load scratch type up to 2 Newton. And you can see at this moment everything changes, meaning that coating actually failed. You can also see in the optical microscope, optical images, the scratch is actually, the coating is completely failed. It is scratching through the coating and going into the substrate. These data actually, when processed for depth profile, this is the raw data of depth profile. There are 3 lines, one for pre-scan, scratch, and post-scan. This is a raw data. It means that we didn't take care of the specimen tilt and specimen initial profile. After we process this, level the depth, that means initial pre-scan data is actually flattened to make it horizontal. To take care of the tilt, it shows this. And after making the pre-scan data 0, you see the relative scratch depth. There are 2 lines here only because other one is 0, so you don't need them. And this was actually during scratch, because it was during scratch, load was there, and there was elastic deformation. That's why this depth is more than the after post-scan, where only this depth is only due to scratching. Scratch depth. You can see this. There is a jump here where actually coating failed, and coating was about 2 micron thick. I came to the summary, and I summarize as follows. R&D activities are being vigorously pursued by automobile manufacturers, academia related to automotive and research organizations, and vendors to stand out in the extremely competitive and dynamic global market. Testing of auto components for their quality is a very important activity. UMT TriboLab is leading in such applications effectively. UMT TriboLab is built as a universal test system on the concept of modular and innovative design that covers wide ranges of test parameters and environmental conditions. Integration of intelligent hardware and software interfaces makes it extremely user-friendly, most versatile, and very productive tool for performing tribological and mechanical tests. I have come to the end of the presentations. Now I will try to look for some of the questions you have already placed and try to answer a few of them. And let me look through please bear me, let me look through some of the questions which are here, and I will try to answer one of them. There are several of them, so I need to pick and choose. We still have about 5 minutes, I believe. Uh, inside the okay, let me take one of them. I am seeing spiral test, but he is talking about clutch materials. Uh, yeah, spiral test is for some other components, and clutch materials should have a different kind of testing. It should be clutch testing in disc on disc type of test. I didn't have a chance to present some of the data, but most likely we'll have some data pretty shown and we'll present later. Okay, there is another questions. Let me find out. Hello Suresh, is it possible to measure the weight rate in line with the rotary drive, and is an oil flow inside the rotary heating chamber integratable? Kind regards. This is from Wolfgang with Hager. Thank you for these questions. Yes, it is possible to measure, but if wear is very small, it is very small in the sense less than say 2 micron or 5 micron. It will have a lot of error while measuring inline using our G encoder. How much does it cost? I think our sales personnel will be happy to answer these questions. I do not have the actual figure, but it should be about, it depends on what are the different models you are buying for purchasing. So it could be probably about 90 to 100K, maybe 115K, something like that. Actual figure will be given by our sales representative. They'll be happy to provide you with a code depending upon your applications and the modules you need. Bear me, I'm still reading to the questions and trying to look. Okay. One questions. Can you compare? Okay. Ball on this data, is it possible to measure also the profile of the samples? For example, thickness of the thin film or roughness, like with this data profilers. Roughness can be measured, but it can be done after the testing in TriboLab because it is not in line. You cannot really measure there. You need to remove the sample and put into under a profiler or a 3D microscope. Bruker has 3D microscope as well, and you can measure the profile. There is a question from Martin Repka, and he's asking about, was there an applications where was used engine bearing instead of the block in BOR module, block on ring test module? Were there any problems with adjusting the system? I do not think there should be a problem with adjusting the system. This is relatively new and very improved design of BOR drive, where it can accommodate actual bearing, and bearing will have compliance contact, and it also have recirculating heated oil facility. How is the hot hardness? This is probably the final questions. How is the hot hardness data good to use or report for measuring COF? Okay. Hot hardness data is good to use. Any kind of measurements we do, it is better to report how testing was done, the way it is done, because so much. These tests are actually relatively new, hot hardness test using UMT TriboLab, and we need to report the way it is tested, what ball was used, how loading was done, what was measured, and how this hardness was calculated. Actually, hot hardness is measured using hot rupture test, they call it, at high temperature. And that has a different methodology to use it. You heat the specimen and find out a load at which it ruptures. And from the cross sections and the load, you calculate the hardness value. So it is better to report the way the hot hardness is measured while reporting it. It's good to include all these parameters so that anybody who wants to compare, they can use the actual methodology and compare it. Again, this could be used for comparing different materials. So if we compare, like, say, apple to apple with similar methodology, it should give a good comparison. There is another question. Probably I'll take this is the last one. What is the accuracy of the G encoder? Okay, accuracy is conservatively I'll say about 1 micron. It is maybe sub-micron, but 1 micron. So maybe if you are measuring about 10 micron, you will have probably 10% error in it. If it is more than, say, 20 or 20 micron, you'll have much less error using G encoder. But again, while measuring with G encoder, you need to take care the compliance of the sample, specimens, and table and other stuffs. So maybe we need to run a blank run without doing a test, just find out the compliance or stiffness, and then subtract that value from the actual measurements to get better results. Thank you so much. We have come to end of this webinar, and I am sorry I could not take care of all of your questions, but all these questions are important to us, and I will try to address them by emailing all these questions answered within, say, today and by tomorrow, hopefully. And thank you so much for joining and you spending your time, valuable time, to listen to this webinar. Hope this is useful. Goodbye.